Hello, Sauce here. This is a video lesson on graphing and attributes. Attributes are the facts that we can say about the function and its graph. Now, I'm going to work an example. H of x is equal to x cubed minus 4. And following along with this example is not just a demonstration of how to do the problem, but I'm also going to model good habits of thinking and setting up and showing the solution process that will eventually save time and lead to more correct and thorough answers for most of the math that we do. This equation it's a function we call h. H of x is equal to x cubed minus 4. And in this demonstration of graphing, I'm going to use the reliable table method for creating points, which we'll then plot and graph. And this is time-consuming and a little tedious, but it's reliable because it always works, and it doesn't depend on technology. So the table method, or the t-table method of graphing, choose a column for the input x and a column for the output h of x. Make some initial choices for the values of x. I prefer these 4 values because they're easy numbers to work with, and it includes a negative and often a very important number, 0. Putting or substituting these values of x into the equation, we'll find h. The first value I'm going to substitute is 0 because it's often the easiest to work with. When I substitute 0 in for x, I get 0 cubed. That's 3 zeros that are being multiplied. 0 times 0 times 0 is 0. And then if we subtract 4, we get negative 4. I'm going to speed up a little bit. When I put 1 in for x, 1 cubed is 1. 1 minus 4 is negative 3. Putting 2 in for x, 2 cubed is 8. 8 minus 4 is 4. Putting a negative number in for the base of a power is a little tricky because you have to remember that the negative is going to change negative, positive every time you multiply by a negative. So a negative 2 cubed is negative 2 times negative 2 is positive 4. Positive 4 times another negative 2 is negative 8. And then if we subtract 4, we get negative 12. Notice that I'm graphing, but I haven't drawn my axes yet. I'm in the habit of waiting until I see much of the set of what I'm going to graph before I choose to label my axes. I do that because making the axes beforehand, you might make some assumptions, and then what you've chosen as your axes to graph might not match what you need to graph. So if I'm looking at this information, then I can see that I have a negative number with a magnitude of 12. So I've got to create, on the vertical axis, enough room to plot that point. I'm also going to choose to count every box as 2. I'm going to count by 2s to fit that negative 12 in. So I go negative 2, 4, 6, 8, 10, 12, and label a tick mark there, negative 12 on the horizontal, on the vertical axis. I'm going to keep it as integers, so every box is 1 on the horizontal axis. Now that I've prepared my axes and labeled at least 1 tick mark, let's plot these points. Negative 2x, negative 12y is there. 0, negative 4 is there. Remember, we're counting by 2s on the vertical axis. The point 1, negative 3 is 1 over, and then negative 3 is down to about there. And the point 2, 4 is 2 here and up, counted by 2s to 4. Looking at the spread of points, I'm not going to connect them. There's no line that connects all 4 points. And neither should I connect each point that is next to each other with its own little straight line, because the full presentation of this graph is going to be curved. How do I draw that curve? There may not be enough information to confidently graph the true nature of this curve yet. I can see that it would help to put -1 in, if not some other points, at least -1 to find the value to plot one more point to help me graph the curve that's going to go here. So if I put -1 in for x, -1 cubed is -1, subtract 4 more, I get -5. I'm going to plot this point, -1x, and then 5 down is approximately there. With that final point, you can see that there's some symmetry in this graph. And I know that I'm going to connect these points with a curve. So with these 5 points, I'm confident that I will capture the essential nature of this type of curve. So there's a graph of this h function. What can be said about the h function? What attributes does this graph have? Well, one thing that we could say about it is it belongs to a family of functions, which are cubes. This is a cubic function. So we could simply use the name cubic as one of its attributes. Another thing to say, a common thing to say about a function is its domain and range. The domain is the numbers that are appropriate to put into the function, its input. X represents the input of this function. So what are the possible values that we can put into the function? What's its domain? What values can we cube and then subtract 4? Well, every real number can be cubed and then we could subtract 4. We could put any real number in, so the domain is all real numbers. There are numbers that we could say that are imaginary or not real, and that is a topic for another time. The range, as a concept, is all of the values that can come out of the function. It's all of the values that are represented by h of x. And what possible values come out when you put all real numbers in? You could look at the graph, you could look at the mathematics, and with some familiarity, you can see that any number can come out of this function if you put all real numbers in. So the range is all real. But the way I'm going to express the range in this presentation is an alternative way of saying all real. I'm going to show all real numbers as a double inequality where y represents any value that could be in the range, and all those y values are in between -infinity and infinity. So again, this range is expressing another way that we could say all real numbers. All the numbers for y between -infinity and infinity. What else can be said about this function? Well, one attribute of a function is its y-intercept. Does it have one? Where is it? The y-intercept can be found where the graph intersects the y-axis. And we've graphed it right there. We can see visually that the y-intercept is there. The coordinates to that point is an x value of 0 and a y value of -4. In the table, the y-intercept is here. The y-intercept always has an x value of 0. So when we're going to record the y-intercept, we're really only interested in the y value of that coordinate. So the y-intercept is equal to -4. Okay, what about the x-intercept? The x-intercept as a concept is where the graph crosses the x-axis or horizontal axis, and we can see that it's there. But this location is not crossing at an integer value. It's somewhere in between. We do not want to say crudely that the x-intercept is at 2. It's not. It's less than 2, and it's greater than 1. Where is it precisely? Well, if we can't observe from a graph where it is precisely, we might need to do a side problem, and we'll do that. We want to know the x value where the y value is 0. That's the x-intercept, the x value when y is 0. I'm going to take this equation and I'm going to ask in the table, if the value of the function we know to be 0, then it's the x that we're trying to find. So we're going to set the equation to 0, and 0 is equal to x cubed minus 4, and we ask ourselves, what's x? Well, let's solve for x. I'm going to undo what I see. I see a negative 4, so I'm going to undo that with its inverse, plus 4. What I do to one side, I do the entirety of both sides. These cancel out, leaving x cubed on the right, and 0 plus 4 is 4. To get x by itself, I need to undo this power of 3, or the cube of x. To undo a power of 3, I take the third root of the entirety of both sides. When I do, a cube root of a cube cancels out, leaving x. And on the left side, I need to take the cube root of 4. I don't know what that is in my head. I can't figure it out. I'll need technology in order to approximate this. I could express it exactly as the cube root of 4. The x-intercept is found when x is equal to the cube root of 4. If I want to get a number for the cube root of 4, I'm going to need technology to approximate it. And if I do, I could punch it into a calculator. I've done that earlier, and I get the approximate value 1.587. And the calculator showed me more numbers past the 1,000th place. But to be accurate enough, when you need to approximate, get in the habit of approximating to the nearest 1,000th. That's the third decimal place. And as a general rule, we're going to write this down because this is important for high school and college mathematics, that as a general standard, if you must approximate, do so within 3 decimal places. That's to the nearest 1,000th of accuracy. And only do that approximation at the final step. If you're not in that habit, get in that habit. It's a good habit to be in. Now, when you approximate in science, which uses mathematics contextually, then science and what you're using the numbers for will often dictate what kind of approximation is appropriate for what you're working with. So approximating within 3 decimal places of accuracy is a standard for math. But don't apply that to science. Pay attention to how you're using math and science and what the numbers mean before you decide to what accuracy or what places of accuracy you need to be at. Listen to your science teacher. And it's recommended, highly recommended, that if you approximate it, do it at the last and final step. If you're working with numbers and you approximate early in a multiple step process, then very often that early approximation, when you work other steps of math with it, will get further and further off the exact and true answer. So work with exact values, even if there's something like the cube root of 4, and if you have to approximate it, do it at the final step to get the most accurate answer. In conclusion, these are some attributes that we can say about this function. There are many, many more things that could be said about the nature of this function. But we need to learn more mathematics and eventually calculus to be able to thoroughly describe this function.